Thank you for the organizers for the great conference. I have little experience up until now, but it's really one of probably the best I've ever been. So the weather was forgiving, but the mosquitoes were not, so I'm under cortisone. If I stutter a bit, it's not my fault. Thank you. Okay, my work is tied to linear optical setting like Ulysses was. It's on the optimality of doing linear optical Bell measurement when the network you use is supplied with ancillary states of various shapes. The work was done in Paris under the supervision of Frédéric Grossans, and it's published in PRA. Okay, what's unambiguous Bell measurement? So Bell measurements, you probably all know, is a projective measurement on the Bell basis. This is a maximum entangled basis. Actually, everything I'll say works for any other rotated maximum entangled basis for 2 qubits. And unambiguous here just means that the outcome of the measurement should never fail, should never be wrong, but it is allowed to fail with a certain probability. And we want, of course, to minimize this probability of failure. In the spirit of the conference, I'll give you 3 applications in quantum communication. So it's about quantum teleportation, dense coding, entanglement swapping. They all use Bell measurements. And in particular, there's one quantum communication task that is uses Bell measurement as a really key ingredient. Is using, for example, the realization of quantum networks. Each one of these is Bell measurements that is done to perform entanglement swapping between the nodes. And even in quantum computation, you probably know the KLM scheme that uses the feed forwards. But there are also different schemes. For example, in this scheme that tries to produce optical cluster states from Terry Rudolph, you have that each one of these small rounds with a 2 in it is a type 2 fusion gates that is actually very similar to one of the techniques I'll talk about for Bell measurement. So why we study static linear optics? From an experimental point of view, it's easier than full-fledged quantum computing. It's even easier than the KLM scheme because we don't allow feed forward. And this means that it can be really done with tabletop optical elements that you could integrate easily. And so I'm a theoretician, so I'm obviously concerned about experimental feasibility, but I'm more concerned about the fact that there's a simple mathematical framework to work with. More on that later. So what's the state of the art? Up until 1995, we have known the optimal scheme when you don't have any ancilla in the network. Is here we have the Bell states coming in as polarization encoding here at the bottom, and this is a balanced beam splitter 50-50, and these are polarizing beam splitter that and photon number resolving detector. Actually, you don't need photon number resolving for this particular task. You just need photon detector, but it's not the case for the next. For the other interferometer I will talk about. So this scheme is known to be optimal even when the network is supplied with feed forward and large number of modes, but without ancilla, since 2001 by a result of Cansamiglia and Lukkenhaus. Why this gives you actual unambiguous Bell measurement? So what do I mean? I mean that, for example, in the output, you see you have 4 possible you have 4 detectors that can click, and each one of the configuration of clicks. For example, here we have 1001 that I highlighted. It can be used to unambiguously discriminate an input state if it can can originate only for one of the 4 Bell state. For example, 1001 is only originated from the psi minus. It means that when I detect this, I am sure the input state was a psi minus. So what I can't do is, for example, discriminate between phi plus and phi minus with these settings, because you see that all the 2 photon in one mode clicks are equally probable, and they can occur for both of the 2. So Okay. Can we go beyond 50%? For about 10 years, no one tried to see if relaxing the assumption of the theorem of Calsameli and Leutkens namely by adding an ancilla, could have been useful. But actually, in 2011, Grice showed that there is like a scheme of interferometers, each one with a better and better discrimination probability that approaches one discrimination probability, but by using massively entangled state of 2 to the n photons. So the scaling is still linear because you get a 2 to the minus n failure probability with 2 to the n photon, but it's not continuous. So you really have one scheme for each n. So, and notably, while the entangled state used by Grice are very difficult to produce, the first step is a three-quarter discrimination probability Bell measurement, and it's done by supplying the network with the blue lines here that are actually another Bell pair, actually in the 5+ state. Okay? In similar spirit, in 2014, Ewert and Walluke tried to work out different schemes achieving the same goal with entangled state, but in their case, they found that they could operate at least the first two iteration of these schemes with single photons that are arguably easier to produce at the price of having half the efficiency, because here for the in terms of photon number. So the ancilla Grice used for reaching 3/4 is a Bell pair, has 2 photons. The 4 single photons for double 2. So we have some limited efficiency. Very interestingly, and that's what stems our research, they found that with 12 single photons, they can operate one of their schemes and reach a probability that is ever so slightly better than 3/4. It's 25 over 32. And this was can't be really 25 over 22. I mean, the optimal maybe may have been a bit better, or I don't know, when you see these strange numbers, you're prompted to search. So what can we say about the optimality of those schemes? Ideally, we would want an upper bound that is for any interferometer with a certain ancilla, you cannot do better than a certain probability of success. Unfortunately, this upper bound proved quite difficult to prove, but we provide an upper bound only for a certain subclass of interferometers. The restriction we use is that they are polarization preserving, so they preserve the polarization of the input photons. This is a restriction that is motivated only by the proof technique. And in order to relax this restriction and to perform a search for any interferometer, we perform a numerical search that uses some symbolical and numerical optimization techniques. So I'll promise you the proof that I'm going to present is quite nicely visual. How the proof goes for the analytical bound. We have still in the polarization encoding, we have our Bell states inputting the first 2 modes of the ancilla, and the interferometer is represented by U. It is a unitary, and we have all the other modes into an ancilla state that I call epsilon. And at the end of the interferometer, we have this contraption that is actually just photon numbers of the detector that also resolves polarization. What we can do, we can easily, for free, perform a quantum non-demolition measurement. It's only a theoretical thing, not saying we have to perform a quantum demolition measurement on all these photons. And this measurement of on the horizontally polarized photon basis will not change the statistic at the outputs, because actually the statistics at the output already resolve all the information in the photons. But now we can see that if we add a certain restriction on U, the quantum non-demolition measurement on this basis commutes with U. And the restriction we have to add is that U is polarization preserving. Okay? In this case, we see that the quantum non-demolition measurement alone can discriminate between psi plus, psi minus, and leaves ambiguity, so leaves some ambiguity in phi plus and minus. This is not discriminated. So what we are left to discriminate is the leftover ambiguity in phi plus minus plus the ancillary state. And this we can assume it can be done with the full like quantum mechanical maximum discrimination probability between two non-orthogonal states. I'm sure linear optics is not so powerful to implement this, but in some cases it may well be. So this is just an upper bound. And actually, so the optical discrimination probability allowed by quantum mechanics is this. And even if we did this this type of simplification, actually the schemes that we know from the literature are all polarization preserving, and the two bounds that we obtain, one that depends on the details of the ancilla, and one that is a bit looser that depends only on the photon number content of the ancilla, they are saturated by the schemes of Grice, for example. So for under this restriction, the bound is quite tight. But we are not content with having this polarization preserving restriction, as experimentally is really easy to change the polarization of photons. So we built a linear network optimizer, so a program. This, in order to see the workings, we have to go to how the program processes this input and output. So actually, we work in second quantization. We can, in linear optics, we can always represent the input state as a polynomial over the input operators, and same thing for the output state. And the two vectors of the creation operators are connected by unitary transformation, U. And at the end, the measurement of the PNRDs can be represented by extracting the coefficient of each monomial, final monomial, into a multivariate polynomial of the output. And each one of these coefficients will be the probability of a certain detection event to occur. Particularly in this case, they are the Fock state. It's okay. What's the method that we use to optimize? So actually, we fix certain ancilla in the input as input of the program. There is a certain number of photon content and a certain dimensionality of our interferometer, so how many modes there are. And for each one of the four possible input state that we get by stitching by stitching the ancilla with the actual four belt states that we want to discriminate, we work out the output polynomial. We collect the coefficients in a function. This function will give us the amplitude and then modulus square the probability. And all this is done automatically by symbolic computation. Think of it as a certain type of mathematica. So it's it just works without by manipulating the symbols without having any numerics. That numerics will be the actual parameters of the interferometer. And then these functions are coded in C so that they can be easily evaluated. And the figure of merit is a certain figure of merit that is chosen heuristically, I mean, with some ideas, is numerically optimized with a nonlinear optimization method over the unitary group. So little example so that you you don't have to take my word for it. This is how the program treats the input state phi plus, where there's no ancilla. Or actually the program works in dual rail encoding, so in the spirit of KLM. But it's up to some isometries equivalent to the polarization that I used before. So the program will expand each one of the input modes into their output mode equivalent. Will refactor all this polynomial and collect the monomials, and the monomials are arranged into this table. So you see from this table there is quite a lot of redundancy. So I mean the numbers are a bit small, but for example, these two detection events are really almost the same. The amplitude is almost the same. It's connected by, if we can obtain one from the other just by swapping the third column with the fourth column of the unitary matrix. This just reflects the fact that in linear optic, as we can easily permutate without changing the physics, the output modes, we can always reduce the number of independent possible probabilities of possible detection events to the partition of the number of photons, the integer partition of the number of photons in the network. In particular, so you could ask why you do this with a computer. I mean, I did this in high school probably. So it's like time function to input. Not a big deal. Yeah, but yeah, maybe it's true. I mean, for a small scheme that recovers the 3/4 Grice discrimination probability scheme, we have the total number of function is about 1,000, but the number of independent one is just the partition of 4, is 5. So yeah, I could have input them just by hand, but actually this escalates quickly. So just the second iteration for the 7/8, that is like 87.5, I think, %. We have the total number of function, it's around 500,000. The number of independent ones is 22, but the number of terms in this independent function is just shy of 2 million. So I mean, good luck inputting by hand. Actually, all this scaling is connected to, as Ulysses was saying, to boson sampling. So it will get harder. Okay, some results of both the linear optimizer and the upper bound, analytic upper bound. So a very important thing to try is how a single photon reacts to this. I mean, can a single photon be useful? Actually, the bound we found only gets you better discrimination probability when we are at an even number of extra photons. So, for example, 1 photon would never be better than 0, and 3 photons would never be better than 2. But that's a bound with a certain restriction. So, how the numerical search does? I mean, the numerical search confirms that this doesn't increase at all the discrimination probability. So, there's no advantage using just 1 extra photon in the network for this task. But with just 2, so with other single unentangled photon, I showed the even one, the polarization preserving bound actually allows a scaling that goes up to 1. Obviously, this is a bound. There's not a scheme for each one of those. We have some explicit scheme that we can work out from the schemes that were already in the literature by changing a bit the setting. And our numerical search stops around here from dimensionality concern. We'll talk about the dimensionality, but actually finds, and this is what we can get away from this slide, is that what should really pay attention is that with 2 photons, we can beat the 50% limit. And this is quite important for schemes that, for example, the Terry Rudolph scheme that use percolation theory for producing this cluster state. There are a lot of protocols in which going above a certain threshold is very important. So we lowered a bit this requirements. Actually, the same scheme that our program finds could be like recovered from the scheme from Evert or Luke from their paper that uses 4 photons just by halving in a certain way the scheme. This is the scheme, and for one experimentalist is some experiments are interested in trying to realize it. It just requires two single photons, some balanced beam splitter and 4 polarization beam splitter and 6 photon number Soviet detectors. Actually, the photon number Soviet detectors may be tightened, maybe weakened a bit. Okay. So single photons seems to help up to a certain point, but do entangled ancilla help more? Yeah, actually, we already saw that 1 well pair reaches 3/4. We find nothing better with 1 bell pair. So it's probably, I mean, the numerical search and the bound confirms that this is optimal. But from, with tubal pairs, it is better than the second right scheme. The second right scheme uses actually a additional JZ4 photon state. We would have been very glad if we had found something, but actually it seems to be no better than one well pair, so we still recover 3/4. And from 3 through n bell pairs, we can't apply the numerical search. It's already too big, even with this cluster that we borrowed from the university. But the polarization preserving bound can be applied and predicts the same scaling as couples of photons, so about 1 over the square root of k. That is actually a worse scaling than the one of Grice that saturates the bounds. Actually, the one of Grice uses very, very highly entangled ancillary state, and this is maybe the reason. Maybe it may be needed to achieve this linear scaling. We would have been very, very happy to test the 7/8 scheme of Grice, and we actually collected some optimization results. Not enough to, I mean, over the course of about 3 weeks, not enough to have good statistics. Maybe some further optimization of the program will do. So I'm drawing the conclusion. What are the achievements of this work? We investigated the optimality of the known schemes, and we explored a new type of ancilla that were never explored before. So we get this upper bound is analytical, but for a certain subclass of interferometer that is like there to be expanded in a future work, maybe. We construct this hybrid numerical symbolical search method that confirms the optimality of the schemes that we already knew, or at least the small schemes, up to some small schemes, and finds puts in evidence a new 2 photon schemes with a 62.5% discrimination probability. Actually, we explored a whole swarm of different type of ancilla because up to until about 6 photons the program works well. And 3/4 really stays the best for these small networks. So obviously this is a numerical search. It may well be that there's something missing, but even with GHZ states, with W states, and quite like crazy things, we couldn't get over 3/4. So some open questions. We should include noise. Actually, everything I said is in the ideal case. In that case, actually, including noise would probably change a bit the question, because you can't really have an ambiguous measurement if you have noise. But actually, there was a paper some months prior of ours by Smith and Kaplan's that analyzed the same question with only single photons as ancillary state, not for an ambiguous measurement, but for just measurement that is allowed to have errors. And they didn't found, at least for single photons, any improvement to our schemes, but for I think 8 more photons in the ancilla, or 6 more photons, where they found a ever so slight improvement, really like 1 over 32 or 1 over 4 or 64, I don't remember. So maybe relaxing the unambiguous case would be useful for the entangled ancilla or for single photons. A good thing would be to adapt the scheme for state generation. State generation is a task in which you enter some states in the input linear optical network, and then you herald the creation of another state with a certain probability by measuring some of the output the output photons. The program as now has to be really modified, because the performance will scale a lot worse with this, because we employ some tricks that works only if we measure all the photons in the end. But it's really interesting. It can be used. And then, as I said, the photon number resolving detector assumption can be relaxed. There are some cases in which you don't really need, because actually, if you just, for example, in the Braunstein-Meyer scheme, you actually only have so you actually only have 2 photons. So if you get 2 clicks, you're sure. You're sure there's no click in the other. If you get 2 clicks in one polarization in one detector, and you don't get click in the others, you don't need to know that there were 2 photons in one of those. You already know from the fact that you don't see photons in the other detectors. And actually, I think that I did some tests but there's nothing conclusive. By enlarging the network, enlarging the dimensionality of the network, you could relax a bit, so convert some of the polarization photon numbers of detectors in normal photon detectors that are only threshold detectors. So it's question time, but first I have a question to the audience, to whom is interested. So we have this automated second quantization simulator that we built, and the code is on the archive and on PRA. It works quite reasonably in a laptop, up to 10 modes and 8 photons. Are there other interesting linear optical tasks that you may want to use this code for? And I thank you for the attention.
Thank you. That was a very interesting talk. Do we have any questions for Andrea? Yeah.
So hi, thank you for the talk. Actually, it's more like a comment than a question. So we should talk about this last thing you said, because maybe we can do fractional statistics simulation with this thing. So
I didn't get the what?
Oh, you hear fractional statistics simulation. There's papers for people trying to use photons to simulate systems with fractional statistics. So maybe this could be a thing.
I have no expertise in that, but it may be useful. The big problem here is the dimensionality. The code is really general, so it works with not only Bell-state discrimination, is general tasks of discrimination, but the dimensionality. It hits very hard. It's worse than than boson sampling, because it's actually boson sampling for each of the possible detection events. So, yeah.
All right, thank you.
So we have time for one more quick question. Okay, then let's thank Andrea again, and we.